Good afternoon, dear students. Now we're having the 18th pre-ultimate practical lesson. So it is related to continuing studying series, and so we know already numeric series, and but there are other different kinds of series, such as functional series, and the most the partial case of them, power series. So this is our topic for today, power series. So how they usually look like. Uh, so uh, so the So the general form of the power series is the following. So the following kind of series, so an, so coefficient, and x in power of n. We need to determine the region of convergence of power series. So starting with it, so 1a, we have the following series. So n starting from 1 to infinity, x in power of n, and by n square. So for power series, so now we will find the radius of convergence. How to find the region of convergence, a radius of convergence? So it will be found by the next formula. So, okay, let me write it down. So the general form. So actually there are two cases. So un, so limit of module un divided by un plus 1. Actually, it looks like a D'Alembert test, but numerator and denominator are vice versa. And what actually interesting for us in this case, so un and un plus 1, so this terms, so not related to x, so coefficients before x. Okay, let me write down u here. So 1 over n square by 1 over n plus 1 square. And it equals 1, and it means that so the radius equals 1. It means that series converges for x from -1 to 1. So actually, so here is x minus 0. But if it was x minus a, so we would have looked the region x so 1 minus a and 1 plus a. And here we investigate the region so -1, 1. So we know that in this integral series converges, but now we need to check to investigate edges of this series. So let's investigate. So let's substitute -1 instead of x. So for x equals -1. So I substitute -1 here. And actually, this series, so we have alternative series, and we know that such series. So let's investigate a series based on modules of this coefficient. So of modules, and we see that it is a harmonic, generalized harmonic a series with a power of 2 that is greater than 1, so it converges. And then, so initial power series converges for x equals -1. And what about x equals 1? So let's substitute. So x equals 1. So we have the following harmonic series. So again, so the generalized harmonic series converges. So it seems that at point x equals 1, series so power series converges. So converges for x from -1 and 1 inclusively. So for both of them. Any questions about this exercise? Okay, no questions. Now let's move to the next exercise 1b. We have the following power series n factorial by x in power of n. So let's calculate this so radius of convergence. So un equals n factorial and un plus 1 equals n plus 1 factorial. So here will be 1, here will be n plus 1, and the limit equals 0. What does it mean? So the radius of convergence equals 0. It means that this series converges only at point x equals 0. So only one point. Any questions about this exercise? Okay. Yeah, by the way, so let's look into exercise 1c. So here, the following series. So minus 1 in power of n, x in power of n, and n in power of n. So for this case, how to find the radius of convergence? We will use something like, something similar to radical Cauchy test. So actually so the radical Cauchy test, we know that we extract the square root. Stop. The root of power of n, but here it is in power, so a root power of minus n. So we divide. So it is inverse value in this case. Yeah, and of course limit for n approaching infinity. So what do I have here? What's going on? So 1 over n n in power of n. So I will receive the limit of n, and it equals plus infinity. What does plus infinity mean? So infinite radius of convergence. It means that the power series converges everywhere. So for each x, it converges. Okay, and once more example. So 1D. We have the following series, so more interesting exercise. So n by 2 in power of n, and yeah, x plus 2 in power of n. So uh, now finding the radius of convergence, but now we will use Downberg test as well. So again, because it's more convenient. So u n over u n plus 1. So writing it down. Okay, so here 1 over n by 2 in power of n. And here will be n plus 1 and 2 in power of n plus 1. So now what do we have? So limit of, okay, n will be cancelled and n plus 1 as well because they're equivalent. And I will receive 2. So the radius will be equal to. And now what do we have? Yeah, so what do we have to do? So so writing down the convergence region. So here we have the shift. So for x, so from subtracting. So from 0, so from from 0 to 4, or not subtracting, but adding these two. So if it was 0 here, so the region of convergence would have been minus 2, 2, but I need to add 2 as well. Oh no, I need to subtract it, sorry. My bad, so minus 4 and 0. And now, and again, we investigated its behavior at these points. So, substituting minus 4. So, minus 4 minus 2. So, it will be equal. So, it will be equal minus 2 in power of n. So, then, so multiplying by 1 in power, minus 1 in power of n. And here will be just 2 in power of n. And now I just remove this and this. And actually I receive the following in a series. So 2n minus 1. So actually it equals minus 1. Or I can even move it here. And we received the harmonic series that always is divergent. So diverges for x equals minus 4. And what about x equals 2? So if I substitute 2, so not 2, but 0. So I have here 2 in power of n, and it will be equal, so minus 1 in power of n minus 1 divided by n. And this is the alternating series. So if I use Leibniz, so let's use Leibniz test for it. So 1 over, okay, so u n Yeah, of course, writing down the limit first of all. So 1 over n, so equals 0. So the first requirement is met. And what about the second? So un, un plus 1. So it equals 1 over n plus 1, and it is less than 1 over n. So this series converges according to the Leibniz test, but it converges conditionally. But conditionally, conditional convergence. So it is enough for this point for this numeric series to converge conditionally. So if it converges conditionally, so this series converges at point x equals 0 as well. So power series, and yeah, and for x equals 4 diverges. So the final answer that our initial initial power series converges converges from -4 exclusively to 0 inclusively. So any questions about this exercise?
Yeah, sorry, I do have a question. So we've calculated the radius and it is 2, but
Yeah.
why do we assume that it converges for x from -4 to 0? Why not -2 to 2?
We have a shift here, x plus 2 in power of n. So we need to subtract this shift from both sides of the interval.
Okay,
So
so if you would just
minus
have x, yeah,
minus 2 and 0 minus 2.
okay. I just didn't take that in count. Thank you.
Yeah, you are welcome. More questions? Okay, if no questions, let's move next to the next exercise. And let's okay, now let's find the sums of given power series using term-by-term differentiation and integration. So, how to do it? So let's start to A. So we will assign actually sum of the series as the function that actually depends on this series. So n from 0 to infinity, and minus 1 in power of n by x in power of 2n plus 1. And 2n plus 1. So yeah, and module of x is less than 1. So actually, it means that the series converges when module of x is less than 1. So now let's differentiate this series. So if I differentiate, I will receive so by differentiating term by term. So okay, let me write down it like this first of all, and then so it equals the derivative of sum equals sum of derivatives. So what I will receive here, actually it will be x in, so minus 1, x in power of 2n. So differentiated. And what else we can see? That, yeah, let's write it down. So minus 1 in power of n. So the first zero term, x, x in power of 0. So it will be 1. And then the first term, so n equals 1 minus x squared plus x in power of 4 minus x in power of 6 plus x in power of 8 and so on. Sorry, just a moment. Okay, so it looks like this. And then we can see that it is a geometrical progression that infinitely decreases. So it infinitely decreases because modulo of x is less than 1. So the denominator equals minus x square. So we will write it like this. So 1 over 1 plus x square. So received the following sum. And then, yeah, if I understand correctly, yeah, so the idea is to write down this sum as a function. So how this function will be found? So s from x. And so now we will integrate this series term by term. So how to do it? So integrating this series from 0 to x. Okay, let me write down brackets here, and I will use variable t here. So yeah, and dt. And then I can integrate actually term by term, each of them. So sum of integrals. But I can do it simpler. So as we can see that it is a geometrical series, I will do just the following stuff. So from 0 to x, I integrate this. So the following expression. So 1 plus 1 over t plus 1 1 over 1 plus t squared. So it will be equal arctangents of t with the substitutions from 0 to x. And it equals arctangents of x. So actually this is the sum, and we also must write down that modulo of x is less than 1. Any questions about this exercise? Okay, if no questions, let's move next. So yeah, let's have more example with, or let's have more exercise with calculating sum. Let's also B. Let's solve B as well. So S from X equals X in power of N divided by N, and modulo of X equals 1. Okay, let me um, erase it. So differentiating this series, and we will receive the following sum. So it will be equal X in power of N minus 1. X in power of N minus 1, and stop. So N starting, N starting from 1, not from 0 in this case, from 1. So again, we have the geometrical progression. So X in power of N minus 1, so 1 plus X square plus X cube, and so on. And again, we receive the geometrical series. The first term is 1, and the denominator equals X. So received the following series. So it converges because modulo of X, so X is less than 1. So okay for us. Yeah, let's check it here. Yeah, so actually the same. So let's integrate this series now term by term. So here will be t, and here t as well. So receiving 1 over n. Stop. We will integrate this expression. So from 0 to x. So from 0 for x to x, we integrate this function. And it equals minus a logarithm of module 1 minus t. And with the substitutions from x to 0, from 0 to x, from 1 to x. No, from 0 to x, sorry. My bad. And it equals minus logarithm of module 1 minus x. But as we know that module of x is less than 1, we can just write down brackets. So we know that under the logarithm is a positive expression. And let's check here. Yeah, so actually the minus logarithm. Any questions about this exercise? Okay, if no questions, let's move to the next exercise. Let's continue. So exercise 3A. So now we will expand the function into Maclaurin series. So actually how the Maclaurin series looks like. So the general form, so we expanded in a following form. So n equals n starting from 0 to infinity. So f, so the derivative of the k, of the order of k. Okay, so here I use k instead of n. So let's do like this. So expanding at point 0 and k divided by k factorial. So doing like this. Actually, okay, so let's just look through this example. So the first way for 3a. By the way, so do you see well everything or not?
Yeah, it's fine.
Okay. So then, okay, let's look through the first way. So in the first way, just finding derivatives and calculating at point 0. After calculating them at point 0, so we see that, so after calculating the first derivatives, we see that some rule, so that f, so the nth derivative equals the following expression. So 2n minus in power of n minus 1 sine over 2x plus n minus 1 by p over 2, so such expression. And received the following series. So minus 1 in power of n plus 1 and yeah, divided by 2n factorial and multiplied by x in power of 2n. And it converges everywhere. But also we can use the standard expansion of sine and cosine. So we know that, yeah, so first of all, let's rewrite sine square of x as, so in this formula, so 1 over 2, so we will reduce the power, so 1 minus cosine of 2x. So 1 over 2 minus 1 over 2 cosine of 2x. And we will use the standard expansion of the cosine. So cosine of x will be expanded by the following formula. So n starting from 0 to infinity and minus 1 in power of n, x in power of 2n, and divided by 2n factorial. And what are we going to do here? So cosine of 2x will be expanded in the following form. So we will just substitute 2x here. So 2x in power of 2n. So we will receive this expression. And I also can write it, so I can move 2 out of brackets. So I will receive, for example, so x in power of 2n and multiplied uh, by by 2 in power of 2n. So now let's write down the initial function. So sine of square of x, yeah, so this function will be equal the following stuff. So 1 over 2 minus 1 over 2 multiplied by this expression. And also I can write down 1 over 2 minus 2. Yeah, so 2n, lost it here. So here will be 2n minus 1. And if we compare it with the initial series, Yeah, by the way, so I can even rewrite it like this. So the zero term of this series will equal 1/2, and I will start numeration from n equals 1. So it will be equal this expression. So this series, and I will just move minus into the series. So under the series, so it will be -1 in power of n plus 1. And if we compare with this answer, so we will receive the same result. Any questions about this exercise? Okay, if no questions, let's okay. This B and C examples, so exercises will be for your home task. So you will do it in your own. And now we will use one. So we will practice have practice with one more kind of expansion. So we will expand into the Taylor series. Actually, Maclaurin series is the partial case of the Taylor series. How expand into Taylor series? Let me first of all write down the general form. So x minus x0. So here I just expand, so I use x0. So x minus x0. So how we will use it? And yeah, and by powers x minus 2. So here we will have x minus 2 power. And Maclaurin series it is a series by powers of x minus 0. Ah, stop. Here will be x0, not x, but x0. And yeah, I forgot x. I lost x here in Maclaurin series. And here will be x minus x0 in power of k. So this is the general form of Taylor series. Okay. So we will first of all write down this, we will rewrite the function as geometric series. So 1/4 minus x. Yeah, and okay, we will use this expansion of 1. So we will use expansion of 1 minus 1/x. So 1/1 minus x equals the geometrical series. So x in power of n. And module of x is less than 1. And we will so this function will be transformed to the similar form. So how to transform it? So first of all, we have to rewrite it like this. So 4 minus x minus 2 plus 2. Okay, writing it like this. And then what I will receive. So it will. So if I expand brackets, I will have 2. Also 1/2 minus x minus 2. But to use this expansion, to use this formula, I need to receive 1 here. So I will move 2 out of the denominator. So 1 over 2. And here I will have, so 1 over 1 minus x minus 2 in power of 2. So received this series. And now I will substitute it into this formula. So this function will be substituted into this formula. So f from x will be equal. So let's do the substitution. So here will be 1 over 2. And here I will use this formula. So this series. And then I will just simplify it. So 1 over 2. Okay. Let me expand brackets. So x minus 2 in power of n. And 2 in power of n. And finally, 2 in power of n plus 1. So actually, this is the final answer. Yeah, and by the way, so in this case, module of x equals, module of x is less than 1, but in this case, module of this expression must be less than 1. And if I expand it, so or x minus 2, module of x minus 2 is less than 2. So I can use the following formula. Any questions about this exercise? So we use standard expansions and then substitute values that we need. Okay, if no questions, let's move next. Let me see what the next exercise. So here we will use limits. Okay, let's solve 5 and we will have a break after that. So 5, so only one limit. So we will have the following limit. So x approaches 0, 2e in power of x minus 2 minus 2x minus x square and x minus sine of x. So we have here the following undeterminate form. So 0 over 0. I know that we can use here so either so consequences from important from perfect limits, or we can use a hospital rule, but the requirement is to use Maclaurin series. So how we will use them? So we will use so we will expand exponent and we will expand sine of x. So we will use the following formula for expansion. Let me write down it here and then here. So e in power of x. So standard expansion that you can find everywhere in any literature. So n starting from 0 and starting from 0 x in power of n by over n factorial. And for sine of x, the following expansion. So n from 0 to infinity, and minus n minus 1 in power over n, x in power over 2n minus 1 over 2n plus 1 factorial. So we will use, so we will substitute these expansions. So, okay, let me move this formulas up. So we will have the following limit. So for the exponent of x, so substituting 0, so 1 plus x square over 2 plus x cube. Okay, it will be enough for x square, I guess. Oh, not how it. Okay, let's use x cube as well. So yeah, and don't use factorial. So okay, but 2 factorial equals 2. So 3 factorial plus so and so on. And what about sine of x? Doing the same stuff. So substituting 0 instead of n. So substituting 0, so x x so x factor x plus x minus x cube stop and starting from 1 here, sorry, or not, and 2n plus 1 here. So then minus x cube by 3 factorial plus x in power of 5 by over 5 factorial minus so on. And now let's expand brackets. So I will receive 2 plus 2x plus x square and plus x plus x cube over 3 factorial and so on. And let's expand these brackets. I will just change signs. Now eliminating members that we, so eliminating what we can eliminate. Yeah, Bogdan, question?
Yeah, sorry, I think you've missed 2 in the x to the power of 3 over 3 factorial. When we
Yeah.
multiply them by 2.
Stop. No, x
No,
x
not but
square over 2 factorial.
no, the next one, like x to the power of 3 over 3 factorial.
Yeah.
Yeah.
Thank you for your attention. Yeah. Okay, thanks. Okay. So now and 2 here. So eliminating 2, eliminating 2x, eliminating x square. I can even write down one more term. plus, so let's write down x in power of 5 here, and here 5 factorial. Oh, let me move 2 out of limit sign for now. And here x is eliminated. And what I actually can see, okay, let's look what is done here. Hmm. Next reduced x. Reduced so next reduced x cube. So we have x cube here. So let's divide by x cube. So 1 here will be square, here will be 1, and here square as well. And if I substitute x, I will receive, so here 1 over 3 factorial by 1 over 3 factorial, so the answer will be 2. So that's it. Any questions about this exercise? Okay, if no questions, let's have a break for 5 minutes. And after that, we will have more practice with using power series. So we will solve the tasks for application of power series. Okay, let's continue. Let me share my screen. So it was task number 5. So now let's calculate. Let's start. Let's solve task number 6. So we are having. So the next. The next uh, tasks. So we will have to calculate the following values with the accuracy 0.001. So how to do it? Yeah, so first of all, we have to calculate sine of 18th degree. 18 degree. Where to use this character? So sine of 18 degree. It actually equals p over 10. So we will use radians. So the expansion of the sine is will be the following. Okay, let me write down expansion of sine. So n starting from 0 to infinity minus 1 in power of n by x in power of 2n plus 1 and 2n plus 1 factorial. Yeah, right. So let's use this expansion. So actually sine over p over 10 will be equal to the following. So I will substitute p over 10 here in power of 2n plus 1. And let's write it down, this expression. So p over 10, then minus p cube over 10 in power of 3 by 3 factorial, and plus, okay, let me copy and paste. So here will be 5, 5, and here 5. And then 7. And so on. So now uh, so how can we prove that we received the expected accuracy? So we need to check if so we need to so we will have to check these terms. So the remainder, so module of remainder must be less than the accuracy. So 0.001. So p over 10. What does it equal? So p over 10 equals this value. And then calculating module of this value. So p cube over 10 cube and multiplied by 3 factorial. So it's still greater than uh, so than the accuracy that we need. And what about the next term? So for what about 5? And it is less than 0.001. So it means that it will be enough to calculate only these values. So sine of p over 10 will be approximately equal these values. And if I add them, I will receive so what I will receive 0.319. So then we don't continue. That's the accuracy that we needed. And now let's check calculators. Stop. No, why? Minus. Sorry, minus. Okay, so yeah, we round, so something like this. So that's how it works. Actually, so in programming languages, how such functions like sine, cosine, expand, and so on, how they are implemented. They are implemented with using power series. So that's how they work. Okay. What about number E? Let's just look through this exercise. So again, we will use the standard expansion for e in power of x. So it is written like this. And then we just, so we need to evaluate the nth remainder. So how it looks like. So the nth remainder is less than 1 over n factorial. 1 over n by n factorial. So we calculate remainder until n equals 6, and then just calculate this sum. And number e equals so 2.718. Okay, so something is okay, so lost the accuracy, but that's not, of course, a tragedy. And now the more interesting task, 6c, we will calculate the integral that we cannot calculate analytically. So where it is, yeah, so the following integral. You actually, so if you start, so I guess you should have seen the similar integral in theory of probability, or a Poisson integral, so that is used in normal distribution. And this integral cannot be calculated analytically, so we cannot use any formulas, so we cannot find it in tables, in table of integrals. So we will calculate it approximately. How we will do it? We will use the standard expansion of e in power of x. So n from 0 to infinity. X in power of n over n factorial. So we will use this expansion. But what about e in power of minus x square? So we will write it down like this. Okay. So Substituting minus x squared in this series. Minus x squared, then it will be equal, so minus 1 in power of n, minus 1 in power of n, multiplied by x in power of 2n over n factorial. So that's how it will be written. So let's expand it. 1, so the zero member, so 1 minus 1, oh stop, 1 minus 1 minus 1 plus okay, what I substitute, by the way? 1 over 3, if I'm not mistaken. Yeah, so first of all, let's calculate the integral. So the integral will be the following. So I will just substitute these values. And then what I will substitute this. And now let's integrate. So it is a power function. So what do we have? So minus 1 in power of n. Then, okay, let me first of all simplify it. And for better understanding for you, so I will move integral into the sum. So under the sum. So like this. And now it will look better. So I will receive the following sum. So n minus 1 x in power of 2n plus 1 n factorial and 2n plus 1 with substitutions from 0 to 1 over 3. So if I substitute 0, I will receive numeric series. Or if I substitute 1 over 3, I receive numeric series. If I substitute 0, I will just receive 0. So 1 over 3 here. So 3 in power over 2n plus 1. Here will be just 1. Okay, let me move minus 1 in power of n into the numerator. So actually, this is what integral equals. And now I will substitute values starting from 0. So substituting 0. 1 over 3 yeah, 1 over 3 minus 1 over 3 cube by 1 factorial by 3. Then plus 1 over 3 in power of 5 by 2 factorial by 5, and so on. Okay, let us start checking these values, if it will be enough terms. Okay, let me write down one more term. So 3 in power of 7, here will be 3 factorial, and here will be 7, and plus so on. So now let's calculate these values. So 1 over 3 of course is greater than the needed accuracy. Then what about this value? So 1 over 3 cube by 3. So greater than 0.001. Then next term. So 3 in power of 5 by 2 by 5. Yeah, it is less than required accuracy. Let's check here. Yeah, correct. Okay, so it will be enough for us to calculate only these values. So the integral will be approximately equal these values. And it will be equal, so 1 over 3 minus 1 over 81. And approximately it equals this value. So 0.321. And let's calculate the integral value of the integral. So with using specialized software. Wolfram Alpha, for example. So integrate exponent of minus x square from 0 to 1 over 3. And we will check the result. So, and it is the result. So approximately 0.321. So this is more accurate value. Any questions about this exercise? Okay, and if no questions, let's move next. So one more exercise. So one more example of usage of series of power series is integration of differential equations. So we will solve the following so in the following Cauchy problem. So y prime equals x y prime plus y. We cannot solve it analytically, so that's why we have to use integration. So that's why we'll integrate this equation with using power series. So it's no chance to solve it in your own. So with any formula, so we will use Maclaurin series in this case. So we have to find the first three non-zero terms of the series expansion. So the Maclaurin series is the following. So we will find it in such way. So the first term actually, so y from 0 equals 0. So we already know the first term. Yeah, and the second term, sorry. Yeah, so y, so this term equals, so y from 0 equals 0 and y prime from 0 equals 1. So now we will find, so we will calculate the value of the second derivative at point 0. So how we will do it? So y prime from 0, yeah, y prime, a double prime from 0 equals, so we will substitute these values. So 0 multiplied by 1 plus 0, so it equals 0. What about the third derivative? So the third derivative is so will be the following. So we will differentiate both parts of the differential equation to find the third derivative. So we will have y prime plus x y prime twice plus y prime. And what about y prime 3 times at 0? It will be equal. So 1 plus 0 plus 1, so it equals 2. So found. Then, so we have two non-zero terms. Then let's calculate the fourth derivative. So the fourth derivative is the following. So y okay, let me rewrite it like this. So 2y prime plus xy prime twice. So we will have two second derivatives plus x plus y prime twice plus x y prime 3 times. And how to let's calculate it at point 0. So calculate it at point 0. So 0, okay, yeah, by the way, so 3, okay, let me simplify this expression. So 0 plus 0 actually, so it is a 0 term. And now let's calculate the fifth derivative. We actually see the rule that odd derivatives are non-zero, but even derivatives are 0. So the fifth derivative So 3 third derivatives plus plus a third derivative and plus x multiplied by fourth derivative. So the following value. And now calculating the fifth derivative at point 0. So the third derivative at point 0 equals 2. So we have 8. And here will be 0. So we have we have first 3 terms. So so this term, so 1, 2, and 3. So 1, 2, 3. So 3 terms. And now we will use the Maclaurin series. Okay, so the Maclaurin series. So let me write down it like this. So let me replace y instead of y instead of f. And writing down these terms. So the first derivative. So 0 derivative equals 0. So the first derivative equals 1. So 1 over 1 factorial by x. Then plus, so skipping the second derivative. And what about the third derivative? Third derivative equals 2 over 3 factorial x in power over 3 plus 8 over 5 factorial x in power over 5, and so on. So actually, this is the approximate solution of the differential equation. Yeah, I also can even simplify it. So let's do it. So let's look at it more understandable. So x plus 1 over 3x cube and plus so 5 factorial equals 120. So 1 over 15 x in power of 5, and so on. Any questions about this exercise? About the whole lesson, about previous lessons? Okay, if not, we will finish. So have a nice day, stay safe, and thank you for your attention. Just a moment. Let me